SPH4U Modern Physics 6.1 Einstein's Theory of Special Relativity. So there are two types of frames of references, inertial and non-inertial frames. So any frame of reference in which the law of inertia holds true, that's called an inertial frame of reference. So all inertial frameworks are equal in terms of adherence to the laws of motion. So the law of inertia is an object that's traveling in a straight line will continue to do so, and an object at rest will remain at rest unless an external non-zero net force is applied upon it. So a non-inertial frame of reference or frames of reference are accelerating relative to an inertial frame. So image B, this shows an inertial frame of reference. So the horse on the carousel is moving relative to its original position. So the original position is basically stationary, and the motion is calculated relative to that. While in image A, the entire carousel is moving, so the entire frame of reference is accelerating relative to this inertial frame. So now here's an introduction to the theory of special relativity. So James Clerk Maxwell had described light as an EM wave. So in which frame of reference is this true? So according to classical mechanics, the speed of light measured through the ether, which is a proposed medium for the propagation of light, should differ from 3.0 times 10 to the 8 meters per second by the magnitude of velocity at which it's moving. The reason they needed to propose the ether was because they assumed that all waves needed some sort of medium to travel through. So scientists Albert A. Michelson and Edward W. Morley wanted to detect experimentally the existence of the ether and if the speed of light changed anywhere. However, they found out that there are no changes in the speed of light across the time of day, the location, or any other factors that could have impacted the speed of light. So they found that the speed of light is constant. So this is where Einstein's theory of special relativity comes in, and Einstein's theory rests on two postulates. The first one is the relativity principle, which states that all laws of physics are valid in all inertial frames of reference. And the other postulate is the consistency of the speed of light. So light travels through empty space with a speed of c, which is 3 times 10 to the 8 meters per second, relative to all inertial frames of reference. So simultaneity is the occurrence of two or more events at the same time. So two events that are simultaneous in one frame of reference are in general not simultaneous in a second frame with reference to the first. So simultaneity is not an absolute concept. So this ties into Einstein's second postulate. From the last slide. So we have Sam, who is stationary, and so event blue and event R, both of them are emitting light waves. So Sam is he's stationary here, so he gets both signals at the same time. So he detects both events at the same time. While Sally, she's on this moving train. So Sally's moving this way. So she detects that event first because she's closer to it, while it takes longer for her to detect the blue event because she is moving she's in a second frame of motion, which is accelerating with reference to the first, which is the frame of reference that Sam is on. So Sam's on an inertial frame of reference, while Sally is in an inertial frame of reference. So this ties into the concept of time dilation. So time dilation is the slowing down of time in a system as seen by an observer in motion relative to the system. So this is given by this equation. Delta Tm is equal to delta Ts over the square root of 1 minus v squared over c squared. So delta Tm, that is equal to the moving observers, time interval. Delta Ts is equal to the stationary observers time interval. C is equal to the speed of light. And V is equal to the speed relative to the stationary observer. So this is basically the speed of the moving frame. So now we can move on to an example. So an astronaut with a pulse of 72 beats per minute is on an aircraft. So what will their pulse be relative to the Earth at 0.9 c? 0.9 c, that is the velocity. So first, let's convert delta TS. Delta TS, we have it in terms of beats per minute right now. So first, let's convert it to minutes per beat. So do 1 over 72. So that is equal to 0.014 minutes per beat. So we know velocity is equal to 0.9 c. So delta Tm is equal to, so delta Tm is equal to delta Ts over 1 minus v squared over c squared. So that's equal to 0.014 over 1 minus 0.9 c over c, all this squared. So c's cancel out, so it's just 1 minus 0.9 c. So this comes out to be, when we do 0.9 squared and 1 minus that, this all comes out to be 0.032 minutes. So we need to find their pulse relative to the Earth, so that's equal to 1 over the 0.032. So this is approximately equal to 31 beats per minute. So that would be the answer. Similarly, there's the concept of length contraction. So length contraction is the shortening of distances in a system as seen by an observer in motion relative to that system. So it's given by this, so we can derive this equation. So delta Tm is equal to delta Ts over 1 minus v squared over c squared. This 1 minus v squared over c squared, it can also be represented by the Greek letter lambda. So I'll just write lambda here for now. So now if we times the time by velocity, so v times Tm is equal to vts over gamma. So therefore ls, so v delta Tm, that is equal to ls, while v delta Ts is equal to Lm. So ls is equal to Lm over gamma. So therefore Lm is equal to Ls times 1 minus v squared over c squared. So Lm is the length relative to the moving observer, and Ls, that's the length relative to the stationary observer. So the subscripts m and s, they are constant in both length contraction and time dilation questions. So we have a spaceship traveling past Earth with a speed of 0.87 c relative to the Earth, and it's measured to be 48 meters by observers on the Earth. So what is the actual length of the spaceship? So you have Lm, that's 48 meters. You have velocity, that's 0.87 c. So we're trying to find Ls. So Ls, that's equal to Lm over 1 minus v squared over c squared, as we could see from this. So Ls comes out to be 48 over 1 minus 0.87 squared. So the same thing that happened in the last question when the c's cancel each other out, same thing happened here. So Ls comes out to be 97.4 meters. So that's the actual length of the spaceship. So now we're going to discuss conservation of mass and energy. So in an inertial frame, we know that work is equal to delta Ek, which is equal to 1/2 mvf squared minus 1/2 mvi squared. So as speeds become relativistic, E total comes out to be mc squared over 1 minus v squared over c squared. So if the object is at rest in this inertial frame, then velocity is equal to 0, and the total relativistic energy is simply E is equal to mc squared. So if we have E is equal to mc squared over gamma, if velocity is equal to 0, then it's 1 minus 0, so the square root of 1 is 1, so that goes to 1, so is equal to mc squared. And now on to the conservation of energy. So E total is equal to E rest. So E rest is E is equal to mc squared plus Ek. So that's kinetic energy. So if you want to find kinetic energy, it's equal to E total minus E rest. So Ek is equal to mc squared over gamma minus mc squared. I'll write out gamma. So 1 minus v squared over c squared. So for an object at rest in a given inertial frame, the total energy is not 0, but it equals its rest energy. So I'll just highlight all the important equations. Here we go. So here's an example of a question that deals with the conservation of mass and energy. So an electron moves at 0.86 C in a laboratory. So calculate the rest energy and kinetic energy in electron volts of this electron. So the mass is 9.11 times 10 to the negative 31, and 1.6 times 10 to the negative 19 joules is equal to 1 electron volt. So first, we're going to calculate the rest energy, then we can calculate the total energy, and then with that, we can find the kinetic energy. So, rest energy. Recall that rest energy's equation is E is equal to mc squared. So, E is equal to 9.11 times 10 to the negative 31 times 3 times 10 to the 8. This is squared. So, this comes out to be 8.2 times 10 to the negative 14. So we divide this by 1.6 times 10 to the negative 19, and that comes out to be 5.12 times 10 to the power of 5 electron volts. So that's rest energy. Now we need to find total energy. Total energy is Et is equal to mc squared over 1 minus v squared over c squared. So this is equal to 5.12 times 10 to the 5 over 1 minus 0.86 squared. So this comes out to be 1.0 times 10 to the power 6 electron volts. So we know that Ek is equal to 1.0 times 10 to the 6, so Et minus Er. 1.0 times 10 to the 6 minus 5.12 to the power of 5. So kinetic energy is equal to 4.9 times 10 to the 5 electron volts. So that's how you would tackle a question with conservation of mass and energy.